Hi everyone, and welcome to our webinar today. My name is Paul Bemis, and we're going to be working on some material here that deals with CFD modeling for high-density data centers. Before we start the webinar today, there's a little bit of housekeeping I'd like to review. First of all, we are recording today, so there will be a recording of this on our website, on the CoolSim website, if you would like to get it later. Second of all, we are providing certificates for professional development. A 1-hour professional development certificate will be available to you if you would like. Please send me a note if you want one after the event, and I'll have my email address at the end. With respect to questions, there is a questions panel in your GoToWebinar session, your little panel that you see probably over on the right. I find it's best if you could type in the question as we go, and I will queue it up and try to answer it as we go. So the idea here is I try to make these as interactive as I possibly can. I like to answer questions. I know that some of you may be watching it together and it will be a little more difficult for you, but if you could have one person take notes and just ask the questions, I would appreciate it, and we will try to handle it. I'm pleased today to be joined by Julius Neudorfer. He is with us. You may know Julius. He's an author of an article. He does a byline in Mission Critical magazine, and he is also a member of the North American Access Technology. He's the CTO. Welcome, Julius, to our program.
Thank you, Paul, and thank you for inviting me here to this webinar.
Sure, I think we'll have some fun. We've got quite a bit of material to handle in the next hour, so I'm going to go ahead and get right into it. First of all, however, I'd like to, for those of you who don't know who Applied Math Modeling is or who I am, let me just tell you a little about it. I am Paul Bemis. My background is both mechanical engineering and electrical. I have an undergrad in mechanical, a graduate in electrical, have been hanging around computer design most of my life. I grew up designing computers in the Northeast, 128 technology belt, worked for a variety of computer manufacturers, most recently Hewlett-Packard, did electronics packaging early in my career, and then later on did high performance computer design. I then went into the computer aided engineering space and worked for a company called Ansys, and then went to a company called Fluent. So my background is both mechanical and then ends up being a lot of engineering simulation software. I worked for the Fluent Corporation. They were acquired by Ansys in 2008. I spun out of there and took a product private called CoolSim. And CoolSim was something that we had prototyped while I was at Fluent, and it is an application-specific implementation of Fluent, the general purpose CFD code, for the analysis of data centers specifically. It's an airflow modeling tool. It is quite cost-effective. It uses a SaaS model where you build the model locally, but you compute it remotely. It's very cost-effective and works quite nicely. So that's a little bit about who I am. Julius, would you like to just review a little bit of background on yourself? That'd be great.
Yes, thank you, Paul. So North American Access Technologies has been around now approaching 30 years, and I personally founded the company. One of the things as a side note that I do is I'm a instructor for the United States Department of Energy Data Center Energy Practitioner Program, which is focused, obviously, as the name implies, on improving energy efficiency in both government data centers as well as commercial ones. As Paul mentioned earlier, I write my Hot Aisle Insight column at Mission Critical magazine, and I think that's approaching close to 10 years now. So I've been around more years than I care to mention. As a company, we've done a lot of different projects and technology development for data centers, telecom, etc. And our specialty really is high performance cooling, high density cooling, power, fault tolerance, and overall energy efficiency in data centers. We do surveys, optimization, etc. And enough self-praise here. I'll turn us back. Paul, why don't you take us through some of the CFD stuff?
Great. So what we're going to do today is we're going to take a look at a non-raised design, Julius. And the reason we're doing this is I see a lot of this. Now, In the business that we're in here, we see an awful lot of designs come over our desk because often there's an issue with them, and we help customers work through it from a CFD support point of view. So I've seen a lot of these, what I call free airside designs, or they're often overhead as well, and they use a plenum wall. Oftentimes in these designs, the air is all coming from one side of the room. So unlike a raised floor design where the air comes in and gets distributed through a plenum with effectively holes in it, diffusers in it, called grills usually, floor tiles. This one has the air all coming from one side. And there are some issues here that people run into that I have seen a few different times that I'd like to review today. And these are very common in what are called free air or evaporative. Things like Kyoto overhead units or enthalpy units or Munter's evaporative units all are used in this kind of design. It is not uncommon for them to use some kind of containment when they do this. Typically, it's hot aisle contained. So the example I'm going to be using today is a generic data center, and we're going to use hot aisle containment. We're going to flood the room with cold air, force the hot up into the ceiling or out of the room, depending how you want to say it or look at it. And take a look at some of the issues that are often encountered, and also talk about how to model it in CFD. So here's the design, Julius. You and I have looked at this a little bit, and there's a few things about it I'd like to review. First of all, let me point out that this is a non-raised design. These blue items that you see along the left-hand side are representing air coming straight down into the supply plenum. I see this often when particularly they're on the roof. Now, I haven't modeled up here, Julius, the equipment that's above the room. In other words, this could be a free air system. In other words, this could be coming straight from the atmosphere down here, and these grills dumping straight into the atmosphere. They could also be Kyoto units on the roof or Munter's enthalpy units on the roof, things like that.
You make a good point, and I think that's a good clarification for people watching this, because right now this is agnostic to the type of system that's handling the cooling. This is more about the airflow within the white space, effectively.
Exactly.
It's important for audience to see the differentiator. We're not going through the complete air cycle.
That's correct. What that allows you to do is model it a couple different ways. Let me point out one thing about this is it's a fairly simple approach. In other words, if you try in particular in CFD to do everything up front, you often get sidetracked with respect to complexity, and you can't get the thing to run, or you're having problems in meshing and it gets frustrating. So what I advocate to people is start off with a simple approach, a simple design, get it to work, begin to understand the flow dynamics in the room, and then turn up fidelity, complexity, whatever you want to call it, detail, to match the needs you have. And I think it was Einstein that once said, a model should never be more complex than it needs to be. Or I think the way he said it is, a model needs to be as complex as possible and no more complex, not more. In other words, only model it to the detail you need. So you are right, Julius. In this case, what we're interested in is what's going on in the white space. So in this model, these are downflow units. They're simply air handlers that I have here along the edge in blue. You see airflow indicated with an arrow. And what I've done in the model that you'll see later is I've fixed the supply temperature to be a certain point. So I'm going to use fixed supply temp to model this thing, and I'm looking at airflow. And this allows us to crank that supply temp up as high as we want and see what happens on the worst day of the year, which is what you want to do with these kinds of models.
Paul, you make a point, and one of the things that I've seen lately in some of the presentations, and they're titled in my mind, and which is backwards. I've seen presentations called tower to chip, and that's exactly the opposite of where you should start, which is start at the chip and work your way outward, because that's really what you care about. Mm-hmm. So if you're worrying about your cooling tower, that should be the last thing on your agenda. Make sure you've got the air going from the chip outward rather than the tower downward.
Exactly. And we have to make some assumptions about the fact the cooling tower will behave itself according to the specs they were provided, right? So we can ignore it for the purposes of modeling because we know it's going to behave itself within the specifications that the designer set in place. One more thing before we go, I want to point out, you and I talked about this a little bit, Julius. This is a steady state model. CFD is often most often used in a steady state case. Now, a data center is not steady state. As it turns out, there are control systems for these units over here always. There's control systems for the racks, the fans in the racks themselves. In fact, these control systems often compete against one another, and you often get oscillations. However, we want to study a point in time that is considered to be steady state so that we understand what's going on in the data center. And that is what we do in CFD. We look at steady state situations, try to understand it, and then use it as a template or evidence to suggest what's going on in the real world. Okay? So that's something that I just wanted to point out. All right.
Indeed.
So this is just the top view of it. Again, these hot aisles are indicated here. These are ceiling grills. So this could be exhausting its air directly into the atmosphere, or it can be going up onto a roof plenum and through an air handler of some kind or an evaporative unit of some kind. There are some obstructions in the room here. We've got some blocks in place. This is the supply wall, the top view, and this is usually a screen or a mesh that they use to try to even out the air as it goes across the room. And that's what this particular one looks like. The specifications for this particular design is this is roughly a 3 megawatt design. And what CoolSim will do is give you a summary report like this that kind of outlines the basic parameters in the room, how many grills, what the size is, but most importantly right here, what is the airflow? How much air is coming from each of those air handlers? And this is a sum. So these are 60,000 apiece. So we're getting a total of 470. The rack load is a 380. Now we'll touch on that in a moment, but you see here we're delivering much more air than those racks need. This is normally done because of N+1. You want to ensure that if an air handler is down, you still have enough air to be able to handle the room. And you want at least enough. So we want at least 380. But if we only had 380, we would have to assume perfect distribution of air in the room. So often it's a little more than 380. You see in this case, even if I took one of the units away, I'd still be at 41, 410,000 as opposed to 380. I'd still have a margin there. Okay. Now, as it turns out, we have to predict what these racks will demand. Okay, we're predicting 380. And the way we predict it is we use the basic heat transfer equation, convective heat transfer equation, to determine that. So let me go through it. First of all, here's the CRACs. These are all set at 60,000. I'm assuming a supply temp in this case of 70 degrees. The 70-degree supply temp represents the upper range of where I want the design to operate. It's arbitrary. I could make it 80, I could make it 75, but in this case, I'm making it 70. The cooling units in this particular model are being assumed to be perfect cooling units. In other words, no matter what the temperature of the air comes back to the map, they're going to deliver 70 degrees. Because, you know, if you're using outside air, for example, it is perfect. You're going to always have 70 degrees because the atmosphere is large. So you're going to get that.
From Maine to Miami, it just
That's right.
appears.
You get the whole thing. So over here on VFD, I'm activated. So I'm using VFDs to control this particular design. So what I'm trying to do in this one is have a positive pressure differential between cold and hot. That's generally what you like to achieve. Now, with respect to the racks, what we've assumed here is the racks are ideal, that they are not leaking, that they're generating 8 kilowatts per rack, evenly distributed across the rack. You can see the delta T's we've assumed here are a range of 23 to 25, and therefore the airflow is, you know, running around 1,000 to 980 cubic feet per minute. These relationships. Go ahead.
Sorry,
Go ahead.
don't mean to cut you off, but what you just pointed out there, and I'm not sure if the audience is fully aware, is that everybody has this wild assumption that magically, especially just mechanical system designers, that their default 20-degree delta T on their air handling units is magically the right number, and when in reality, there's a wild variation on the IT equipment going on.
Yes.
Both in different models, different densities, as well as even while they're running, they go through different delta
Exactly.
T's. So
Exactly.
this is where CFM really begins to pay off if you know your equipment.
That's right. And getting to know the equipment is challenging because, as you pointed out, it's got a controller in it. It used to be when I did them as a young engineer, they were fixed speeds, right? And we always designed them for worst case conditions. So often your delta T would be 5 degrees because the thing would be blowing air like crazy. And some equipment in your data center may still be like that. At the same time, the newest equipment that's coming out is seeing delta Ts of 30. Or 35 degrees Fahrenheit. They're actually producing much less air. So yes, this is an assumption, and assumptions like anything are subject to interpretation, but we have to start somewhere, right?
Absolutely.
And what this does is it says, in order to cool 8 kilowatts of power, I need at least, look at the top line, I need at least 1,072 CFM for a 23-degree delta. That's simply the heat transfer equation. That's what it falls out at, convective heat transfer equation at sea level. By the way, it does vary with altitude, and there's an altitude set in the program that allows you to set the altitude, and we're assuming even distribution of load. Now that's another assumption, right, Julius? It's not always even. Just because I have 8 kW doesn't mean that it's all located evenly distributed across the server, across the rack, right?
Right.
Yeah. But again, you have to start somewhere, and this is a good place to start. Now it's oftentimes all you have, because if you're doing a new design and it hasn't been set up yet, you don't know what's in the room and you don't know what's going to be in the room. So you have to use some kind of assumption, and this is as good as anyone to get started. So we're going to assume the containment does not leak initially. This is another thing that you have to determine, is how do you handle the containment. We're going to assume the rack demand is linear to power load. In other words, as the power load goes up, the CFM goes up with it in a relationship that is linear, which is not really true, but in fact, we have to make some assumptions in order to do anything, right? The racks are ideal with respect to uniform loads, and there's no leakage in the rack. The racks are on the floor. There's no gaps under them. VFDs are turned on, and I set it to 0.01 inches of water differential pressure between the hot and cold side. So, all right, question just came in, Julius. How do you know how much temperature drop to expect for different manufacturers? Again,
That's a very good question. I think I'll just take a little whack at that just for what it's worth, because it's one of the things that I run across with on an almost daily basis when we go into troubleshoot, and that is that you don't. But the way you can get close enough to it is most of the major manufacturers have a tool which will allow you to generate a CFD estimate based on the worst case and best case conditions, meaning the lowest and highest CFM. And where that really particularly jumps in at you is when they have the newer IT equipment with energy efficiency modes, the fans are normally set to suppress to optimize their energy efficiency, so they will run as slow as possible before the chipsets begin to reach thermal barriers. And so you tend to run higher and higher temperatures. You'll see that in particular with all the high performance blade servers.
yes.
So the assumption of these 20-degree delta T's are really a dream. You really, as Paul mentioned, they're running in the 30s, in some cases even as high as 40 plus. So go to the tool and see what the vendor says, and you'd be surprised.
Yes, and I have seen the Dell tool. However, it is configuration dependent even for one package. So it does vary even within one package, the CFM.
Yeah, within the same package, you have to actually plug in what blade you have, what processors, etc.
Yes.
And they've run into this problem so many times that they don't want to have people kick the equipment back. So there is a great deal of but you just got to go to the vendor tools.
Yes. That's if you know what you have in the racks.
Yeah.
Right. The other point I would say here is assuming a lower delta T is conservative from a design point of view. In other words, a lower delta T is going to give you a larger airflow and on the rack. And if your air handlers can handle that, then chances are it's going to be able to handle the other end where they're consuming less. So yes, 25° F is sort of the middle of the road. It is an assumption, but it's a fair one. We just moved the default on CoolSim up to 25 from 20 so that it's a little more in line with current trends. And we'll probably move it to 30 in the next a year or two. Okay, so let me first take a look at the results of this, and I'm going to pop these results here. They're going to open up. This is a set of CoolSim output, and CoolSim allows you to export the entire set of results into an HTML doc. This is the same thing that you'd see inside of CoolSim, but here we're running, of course, just through a browser. If you look, I'm just staring at my desktop. And the first thing I want to show you is the VFD report, and you see here I tried to set that value to be 0.01 of a set point, and I'm running negative. So this is kind of interesting. You see, I maxed these out at 50,000 each. I set the upper limit on 50,000. It's really 60, but I knew I wouldn't get to 60, so I set them at 50, and it went right to the top. And so if we look at the CRAC report, we see we're delivering 400,000 CFM in total. And if we look at, again, the demand for this space, we see that it's 388. So we're delivering 400,000, Julius, on a design that's at 388. But take a look at the pressure plot. This is kind of interesting. If we take a look at pressure, here we'll take a look at it at 5 feet, and look what we have. So here's the pressure plot.
Very
now
interesting.
Yeah, it's upside down in the sense that you would expect, if we're overdriving the cold side, and we just saw we were, that the cold side would be running at higher pressure, and it's not. The hot side's running at higher pressure. And that's a surprise. No leakage anywhere. I'm not leaking. It's a perfect seal. So that means I should have more pressure on the hot side.
Mm-hmm.
And part of the reason I do this webinar today is because this is what I see sometimes. And people ask me, well, why is that? So question for the audience, why is that? Now, you don't always know. I mean, it's not always evident exactly why this kind of thing occurs. But the wonderful thing about modeling tools is you can experiment with parametric variation and understand why. In other words, try something, figure it out, look at different variations and see. So what we did here is the first one showed that, and the question becomes why? Is it ideal gas law? In other words, it's hotter, right? We're 25 degrees hotter on the hot side than we are on the cold side. We know hot air gets high pressure, right? So is that it? Or is it difference in supply return volumes? If we go back and take a look at the model itself, this is the input model here. You notice that the volumes here, Julius, of the input and the exhaust, see, we've got right now a 12-foot ceiling above those. It's 10 to 12 feet. Okay, and if you look at the hot aisles, they're only 4 feet wide. And I see this sometimes where designers tend to starve the hot side a little bit. So the first question I would have, or the first thought I would have about this is, are the aisles too narrow, right? Because we've got hot air coming blasting out of there. Let me just bring back here and I'll show you that hot air. The hot air is coming out. Let me show you the air coming out of the racks and PDUs here. Take a look at this, right?
Yep.
I mean, we have a lot of air coming out, and look how it's beginning to wrap up on that ceiling like that. So it's banging against the top and swirling before it gets over to the returns. Now, if this were a free air system, I would argue would make this ceiling just huge, make it really large so that you don't have any effect from that. But also, look what's going on inside this aisle. I mean, and we can get a shot of it here. That's this little viewer allows you to make it kind of nice to look at. But
that's very convenient. You can really break down each component and get a much clearer visualization.
So there's two pieces here I want to suggest. One, people tend to forget, Julius, that pressure is the sum of dynamic and static, right? It is the sum, right? Total pressure equals the sum of static pressure plus dynamic moment caused by momentum. Look what's going on here. We've got air coming blasting out of here and turning this corner and going up. So there's an awful lot of pressure being built right in that region as a result of the fact that this air is moving. Now, the fact that it's hot aisle means you've got buoyancy in your favor. That's helping you. It's a chimney effect.
Mm-hmm.
But these aisles are pretty tight.
And the funny thing is you're using a 4-foot hot aisle as opposed to many places using a 3-foot hot aisle, using the 4-foot for cold aisles and 3-foot for hot aisles. And you're actually at a 4-foot hot aisle, which gives you obviously 33% more surface area, or not surface area, but opening area.
That's right.
So that's even more of an eye opener, if you will.
That's right. So what would happen in a case like this is if you had any leakage anywhere on the containment or the rack, it's going to blow right through it. It's going to come back into the room because the hot side's got more pressure.
Right.
So what you can do as a result, you can test it. So what I did here is 3 sets of results. In the first set of results, we tested supply air temp. So in this one, what we simply did is to change the supply air temperature to be colder and see if the pressure variation changed. And if I quickly take a look at the pressure variation at the same exact height, we find, remember that we were up at 0.2 to begin with. So we were running at a high pressure of 0.2 on the last plot and pretty close to 0.3 at the bottom. So temperature wasn't really the parameter. It wasn't temperature. So now let me take a look at increasing the aisle width. This one's kind of interesting. So here what I'm doing is simply looking at the same exact design. Let me show you what the shaded model looks like so you can see it. So there's the model there, and you see those cold aisles, those hot aisles are now wider. I increased them by a foot, I believe, each one of them. And what we want to see, with the ceiling the same, supply air temp the same, everything the same, what effect did it have? And if we take a look at that cut plane again at 7 feet, look at the top range. Now it's still red because what it does, people who don't run CFD often get confused by this, but what I have is we take the min and the max and we spread color out across it. So where before we were running at a range of 0.2 up here for high pressure side, look at that, Julius, we dropped to 0.09.
Yeah, that's a big difference. You still got the same scale colors, but of course it's a whole different numeric value.
That's right. So it dropped quite significantly. So width makes a difference. Now let's take a look at those path lines again, same ones I was looking at before just to show them. And again, I'll zip this thing around and turn off perspective. And so you can see here, it's just helping quite a bit with respect to that same parameter. In other words, we now don't have quite so much problem with respect to the momentum because we've just got, you see, it's just, there's fewer path lines, there's less crowding going on there. I'm still a little uneasy about the ceiling, but
exhaust fans.
Yeah, well, yeah, or something, right? But at least we find that a sensitive parameter is aisle width, and I'd like people to be aware of that. You've got hot aisle, right? So pressure is going to be there because you got some temperature effect. Furthermore, you've got the fact that these racks are pointing at each other. These fans point at each other, and whenever you have to redirect air, essentially move it, turn it, slow it down, redirect it, the pressure is going to rise because it's going to turn into static. Yeah.
Now, even though you're doing a static model, the other thing that this points out, and it's kind of interesting, is the fact that we normally, if we've been talking about a raised floor design, we're always worried about the underfloor static pressures, obviously the grill pressures, CFM, et cetera, et cetera. And normally it's perceived in general that the sort of flooded room design, which is not limited by underfloor grills, is the perfect supply model. But what you're really pointing out here is once you go to the no floor, and even though we always like to prefer to pull out hot aisle, contained hot aisle, is that the other effect that's there, you're using your static baseline, but when the fans sense the chips are running at high CPUs and therefore their heat output is maxed, a lot of the software will just drive the fans to 100%.
Yep.
And that will actually force even more air than your static model might show, which exacerbates the problem. So if you see it in the static model at your baseline presumed airflow, the fans wrapping up will of course even increase the pressure even further in the contained hot aisle and the plenum.
Yes, you're right. And we're assuming even air distribution across this rack because I've got even load. So the airflow across the rack is even as well, and that's an assumption as well. In other words, it's not always even, it's chunky, right?
Mm-hmm.
And so I've seen situations where you have, a blade server at the top that's blasting because it's hot. Down at the bottom, you've got something that's not quite as hot, and the air is getting trapped at the bottom because of the air at the top coming across and effectively creating an air dam.
Yep, you're getting higher back pressure at the bottom when you shouldn't
Exactly.
have it, and
Exactly.
because the top is overwhelming it.
Exactly correct. One other thing I wanted to just point out here, and I'll show it in a velocity plot. This is something that I want people to be aware of in these designs as well. If we take a look at a velocity plot, and part of this is just showing you how to read these things a little bit. But here's the air coming out of these air handlers and going down these chutes right here. This is the cold aisle. It's shooting down. And you notice we have high velocity going to low velocity. So we have low pressure going to high pressure. That the pressure in the room is all down here against the wall. That's where the best pressure is because that's where the velocity is lowest on the cold side. One of the things that you should be aware of when doing this kind of work is be careful of the delta P, the pressure drop across these leading edge servers. If these servers get too close to this fan wall or whatever it happens to be, this tangential airflow going across here, Julius, causes the delta P across the units here, the fans, to be so high that these things ramp up trying to pull that air in because it's got to do the same thing. It's got to go around the corner. So I always check them to make sure that they're okay. This one in particular is fairly high here. We're seeing 740 feet per minute shooting down this aisle. So I often take a cut plane of pressure in that Y direction. This one is down around 5 feet. And I try to take a look at, and you can change the scales on these things to tighten them up. But I try to look at what the pressure differential is across these aisles. Now, right now I'm seeing a full range of roughly 0.1, right? So I'm not really too worried about that. But if that number were 1 inch, I'd start to worry about it.
Yeah.
Right? Because that's
if you hear it whistling, you know you're in trouble.
Right. So I wanted to just point that out. All right. So now the other variation I did here, and this is a great use of CFD, is wiggling these parameters to see what happens. This particular set of output here was I kept the aisle constant, and all I did was vary the height of the ceiling. So here, let's take a look at that same cut plane, and what you'll see here is even more effect. So remember, I was a little over this before, just moving the aisles wide. So now I'm 0.01 to minus 0.08. So I'm, 0.1 roughly of total pressure. Now the hot is still a little higher, but now it's so close that it's going to vary as a function of height. And I should be able to now drive my differential across that as a controller, because what I'm trying to do in this case is drive off pressure. Now, I could have driven off temperature as well to drive the VFD, but in this case, I happen to use pressure. So geometry makes a big difference, and you see the height there. I think I moved it up to 20 feet. Geometry makes a big difference, and one of the things you want to be sensitive to is what's going on the hot side on a design like this. You can, flooding the room is fairly straightforward, but even air distribution in the room due to velocity variation, and also what's going on the hot side. Don't starve the hot side. Give it enough room to breathe.
Yeah.
Would be my comment.
Absolutely, yeah. The flooded room is normally an ignored parameter because once it's flooded, they consider it everything is the same, and to a certain degree, it's certainly a better solution than just worrying about each tile, no question about it. But it's not a perfect solution, so your model shows that clearly.
That's true, and furthermore, in a flooded room, there's no control over the air. Unlike a supply plenum under the floor, Julius, where you can put a tile in, take a tile out, you're effectively reducting it as if it was a
Hmm.
big duct and changing the diffusers. But here we don't have that freedom, so controlling that cold air can be challenging.
Yep.
So anyway, here's some side-by-sides. When I changed it from 3 foot to 4 foot, we went from 0.12 on the top to 0.09. So if you can't see those, that's a 0.12 up at the top here and a 0.09 we went to here. The low end stayed about the same as you would expect. So that was a big difference. And then when we went to 12 foot, it did the same thing. It dropped to 0.12. 20-foot ceiling went to 0.01. So that's quite a difference. So it looks like the ceiling had more effect than anything else than the wide aisle, and that was starving it a bit. Okay, so geometry on the hot side is important, and I want people to be aware of that and be sensitive to that. So now let's go to leakage. I've been assuming no leakage so far. I've been assuming perfect racks. That's not always the case.
Indeed.
It's not often ever the case. So here we have a situation. I'm going to assume here the customer has said to us, assume 5%. Now I get this a lot, 5%. And the question I always ask you is 5% of what, right? Is it 5% of the total airflow coming in on the cold side? Is it 5% of the total containment surface area? Is it 5% of the rack surface area? The problem with percentages is kind of that. Do you know what I mean?
Absolutely. I mean, and usually they're just pulling a number out of the air, frankly, because when you ask them for something they don't know,
They
it
don't
seems
know.
like a good number. I heard that before, so I'll use it again.
Right, right. And they know it's leaking a little bit, but they know it's not 50%. You know what I
Hmm.
mean? So anyway, I tried to parse this a little bit. I said, all right, if a customer says to you or the design spec says 5%, how would you do it? One way to do it is to say the 12, I went back to 12-foot ceiling, assume the containment leaks at 5%, but the racks are still perfect. Now, the problem you run into when you do this kind of thing is the pressure differential across that contained area tends to vary. And as a result, when you do percentage of leakage, you get different kinds of numbers. Let's go to a pressure map again. I'll use 7 feet again just to show you. And one of the things you'll notice here right away, and let me just go to the Y and take perspective. We're looking straight down at it. Now all of a sudden, things begin to look like we'd expect them to look. So the hot aisles are now running just a little bit lower,
Hmm.
right? I'm
Yep.
sorry, yeah, a little bit lower than the cold. The cold is running at a higher pressure, and that's what we'd expect. And the reason that that's true is they're leaking, right? The air is coming out. If we take a look at, for example, a thermal cut, let's take a look at temperature at 6 feet. You see what's going on. Watch, let me flip this up. Okay, we're getting contamination. It's coming into the aisle, right? It's leaking. It's coming out of the
Absolutely.
containment and coming straight out. And it's leaking quite a bit on the ends. You see the cold air being pushed in there on the ends due to the high pressure caused by the air coming right to the end and banging into that end cap. So doing leakage on the containment is a fairly good first order approximation, but
Hmm.
it's not linear. In other words, it varies depending upon the delta P, delta
Hmm.
pressure at the various points, and so the leakage will be non-uniform. Not bad. I often use it to get started. It's a good place to start. It's a good place to start your sort of investigation of how the design behaves, but it does have some limitations. So we have another one here where, and this is just a summary, most containment solutions, by the way, are made of hard material, so it's not porous. It's not really appropriate to let it leak everywhere. Another variation on this one, Julius, is I'll allow sometimes the end cap's not the leak, but I'll let the surface above the racks leak a little bit. You know what I mean? In other words, be specific about where you put your leakage would
Right.
be.
You have cable issues going on because instead of cabling coming under the floor, you now have cables coming in on top. So by nature, you tend to have leakage because you have an imperfect seal, no matter even if you use full corroborating. So
That's right.
you have to acknowledge that in the design.
And you can set these, like this one right now is set not to leak, but you in the modeler can set these to any percentage. Again, this is a percentage leakage. It's a porous
Hmm.
coefficient, but you can set. So oftentimes I'll have the end cap solid, but I'll let this upper section leak a little bit. That's a good one. But a more detailed one is to get into the rack. And a couple of questions have come in about this already. Um, in this case, I'm going to show you, I said, well, let's take the surface area of the rack and let's make it 5% open. In other words, if the entire rack row consists of a certain cross-sectional area, let's take 5% of that cross-sectional area and let's let it leak. Let's make the containment perfect. In other words, let's make the containment out of blocks or turn leakage off,
Hmm.
because generally speaking, the hard surface doesn't leak. Where it's leaking is in the rack or around the rack or under the rack. And
Absolutely.
what I did here is I did 1U openings, and I used this little tool called Rack Builder. So this is what Rack Builder looks like. It's essentially an Excel spreadsheet. You open up the tool itself, and we give you an Excel spreadsheet. So the idea is we're looking directly at a rack row. You see each rack is here as a column. And
Hmm.
then each one of the little cells in your Excel spreadsheet is a U. A U is 1.75 inches. So you can either make a U a gap, or you can make multiple U's a gap. So what I did here is came up with a prototypical rack row where I spread the load around sort of non-uniformly. You can see I've got blanking panels in some areas and load in others. So I kind of randomly distributed the load, which solves the issue, Julius, of uniform distribution of load, which isn't real. This is a little more realistic, right?
Hmm.
And also I put gaps in there, and the sum of my gaps altogether, if I sum them up for a rack row, represents 5% of the cross-sectional area of the surface area characterized by the rack row. That's what I did, and I put
One
it
of the
into the model.
things you and I chatted about before the presentation here is, and this is a common thing, is people are now finally, most people are finally now acknowledging the value of containment and blanking panels. But still, the open area issue is still the side walls. So in other words, you have
That's
the
right.
vertical openings, which are just barely being thought about by most, and only a few people are. And especially if you're talking about containment and pressure, there's a 1 to 2 inch gap on each side of the rail that is essentially open,
That's
and that
correct.
that becomes a substantial surface area, or an opening area, I should say.
Yep,
So even if they perfectly put blanking plates in place, horizontal blanking plates, there's still open areas that, of course, in the tool you can model by including a percentage higher than 5, for instance.
that's right. So I'm going to try something here that I've never done. This is a new feature of this GoToMeeting, and they allow you to create a little video. So I created a little video. In this short video clip, what I was trying to do here, we ran into audio problems during this section, so I'm just annotating it. But what I was trying to point out here is that in CoolSim you are able to open up something called Rack Builder, which allows you to create a panel or open a panel that looks very much like an Excel spreadsheet. And in that spreadsheet you are then able to define just exactly where the load is in the rack, and also along with gaps and blanks. So here I'm defining a server. Each one of these little cells is 1U of height. So I've just created one that's 8 U's. Here's another one that's 11 U's, and I can use this to actually put the load just exactly where I want it in the vertical surface. I can also put gaps in place, which I use to model open area. Here I'm doing it for another rack, just putting in load and then putting in either blanks or gaps. In this case, I'm putting a gap in place, and then further down at the bottom of the rack, I can put in another server and distribute that load non-uniformly. In other words, it's no longer a uniform load across the rack. It is something I'm putting in explicitly. Now I'm doing it fairly randomly because it's supposed to represent some random loadings of the racks in the room. So there you see I've changed it from being uniformly loaded to specifically loaded.
Paul, we've lost
And
your
I have
audio.
also put gaps in place that now model the airflow through that rack, the leakage through that rack, explicitly instead of as a percentage. Can you hear me? Am I okay now? Test 1, 2. Huh.
We're good now.
Good now. That's weird. Weird, huh?
Yeah, both our mics dropped off as soon as you went to the video mode.
Okay.
All right,
Well,
we're back.
we're back. Like I said, it's the first time I've ever used
First
it.
time. All right.
This is a little cloning feature here I wanted to show. Once you've done one rack row, you can do the others by simply putting in something called clone, and you take that one rack row that you've done and you can clone it across the entire data center. So this is a copy with offset feature inside the modeler. And the benefit of that, of course, is it just allows you to do things really quick. So I laid out that whole data center there, at least in terms of the rack rows on the left-hand side with one click of the mouse. All right, so we know the audio stops when I start to run these things. I'll be aware of that next time through, and we'll go back to our...
Need a little upgrade in the software there.
All right, so that's what the resulting rack rows look like, and let's take a look at the results that way. And what we're going to find, I think, is that things begin to look a little more appropriate. So let's just take a look at that cut plane again. We're going to go pressure at 7 feet, and you see things begin now to behave themselves. You see here I'm running at lower pressure.
Oh, we don't have your screen.
Huh. Yeah.
Lost the PowerPoint or this. You know, you're on a broadcasting screen right now.
Yeah. Thank you. Let me. Again, this is just getting to know how to use this little system.
There we go. You're back.
There we go. Yeah. We're back.
For our audience out there, Paul is back.
So here it is again. What I've done is I've taken a look now at pressure, same cut plane, and I'm letting leakage occur at a percentage that is defined by the surface area of the racks themselves using that little tool I showed you. And what you're seeing here is we've got negative pressure in the hot aisle and positive pressure outside. So the model is beginning to behave correctly according to what we think. I wanted to show you a couple other things here, Julius. You can see some leakage here. If we take a look at a cut plane, let's see if this has one. Yes. Now you'll be able to see here exactly where this one happened to line up. The cut plane lined up through these U's right here that are open. Mm-hmm. And you can see, depending on where you are, leakage in one way or the other. So here we've got a little bit coming out because pressure is not perfect. So you got a little bit leaking this way, but not too bad. In the other cases, you see it coming in. You see it starting to come in from the cold aisle. And that's again due to pressure variation, but a fairly realistic representation of what happens in the real world. Now, I'm going to take the risk running the little video clip again and showing you can go a little higher.
Just remember to unmute once, because it'll jump to mute probably. Let's see what happens.
No, let's see. I don't want to run that one. Let me run this other one. Detailed rack view. Here it is. So
you're muted, Paul. Unmute yourself.
Boy, that's annoying, that little feature.
You know, it's probably expecting audio from the.
I think it is,
and that's why it's automatically muting, because it doesn't want the mics to overload. But now you know.
So to your point, Julius, in this model, I have built an assembly, and here what I have, and let me stretch this out a bit so you can hopefully see it. Here what I have is I've put a rack inside of a box. I've got 2 rails up front. I've got a passive chimney in this case with diffusers on either side of it. I have the rack inside the package flowing front to back, and I've got inside there rail leakage. So you see there's a baffle right over here that's leaking at, in this case, 5%. So we've explicitly put the rail in that you referred to and let it leak.
Wow,
now,
excellent.
Yeah, excellent, except your mesh count goes up, your complexity goes up, it takes longer to solve. Okay, so you can do it this way. You can get into, and here I've used Rack Builder to distribute the load inside the rack. I'm simply showing that level of detail can be increased if you want to, but you do pay a premium, and the premium, of course, is time to solve.
Right, but you know what you can do, obviously, since once you develop the singular model for the rack, you don't have to then force yourself to spend the time for 400 racks. You can then use a more valid assumption because you can model the single rack and then apply it as a rough reference throughout the
That's
design.
exactly correct. All right, so I'm back. Is my audio on? Yep,
Yes,
it is.
you're good.
Okay, I'm good. Except we lost the page. Here we are. Okay. Now, final thing before we open it up to questions, and we're getting near the end here. One thing I would encourage everybody to do is do variational studies on your design to make sure you understand what happens when your air handlers are down. Inevitably, you're going to have one down or two, and depending on the design, whether it's N+1 or N+2, you're going to want to know. So here, what I'm showing you is the ability to run multiple variations, and I've got two of them here. But in CoolSim, you can set up multiple variations off of one model, which is quite handy. So here I've got, as you can see, 4 different runs set up. And what I can do is vary either the volume of the flow or the temperature of the supply air or the on-off state. Now, in this case, what we're mostly interested in is simply the on-off state. We're not really interested in the flow. The flows are going to remain constant or relatively constant. We're using VFD here to drive it. But underneath each one of these numbers here, run 0, 1, 2, and 3, is exactly the full set of results we saw before, including the pressure plots. And what you want to look for is, recommended temperature range. Are you within acceptable range? And you see here that in this particular run, you are, for the most part, within temperature range. I don't know what the specific RCI looks like there. We can take a look under this parameter. So we've got RCI of 100. They're both running at 100. That's a pretty nice design right there.
Yeah, that's as close to perfect you can get. Of course, it may not be there when you get in the field, but
Yep.
on the surface of it, you hit the number.
Yep. And we do see, if we go to full range of temperature, you'll see some variations typically that are a result of those. Yeah, take a look here. You can see the holes are leaking a little bit. You see around the edges of those 1U holes, you'll see a little bit of temperature creeping up, which is again what you see in the real world. So
absolutely.
So I won't take everybody through that because I want to open it up for questions, and we're getting close on time. But I did run them both there and check those out, and I encourage everybody to do that. So just wrapping up, if those of you in the audience have other questions, I have a few here, but most of them are saying no sound and no image. But a couple things, takeaways. Hot aisle containment is great. I advocate for hot aisle containment whenever you can because it gives you more volume on the cold side, but remember, it needs more volume. In the original design that we looked at today, the relationship of hot aisle volume to cold aisle volume was almost 1-to-1. I did the math, I checked it because it was one of the things I was looking at. And the takeaway here is you need to give your hot side enough volume, enough room to be able to expand and for it to go through the momentum change necessary to turn corners and head out through the ceiling. So important thing to keep in mind. I always advocate for a coarse degree of granularity first, of detail. Don't try to get carried away modeling every single thing. It's not a CAD system, it's a modeler, it's a CFD modeler. And if you put in a tremendous amount of detail, you will pay a price in time. And it's more important, I have found, to run with assumptions that are fairly coarse at first and then turn up the fidelity over time as appropriate. The other point I made is don't forget the N+1 variations. You may find surprises there. I did not find any in this case, but oftentimes due to geometry alone, the positioning of these air handlers, you'll find some surprises where one of them is sensitive, and when one of them is down, the others are carrying a tremendous load, or you're not getting air to the service you need and you get hot spots. And I guess the final point is, of course, that it's much easier to do it with a modeler than it is to do in the real world. So let me take a few questions here, Julius. If any of you have any questions anymore, question about a recording. Yeah, there is a recording that we will post, and you'll get an email about that. It'll be on our site. Can you model rate of rise is another question. That's a transient run. The answer is, instead of running all the fans, have them interlocked and find out the long critical temperature time? I get this question a lot. The answer, of course, is yes, but do you want to pay the penalty and price of time to do it? Okay, so let me quickly tell you that in CFD, when we do transient analysis, the way we do it is that we do a steady state run at each time step, okay? So now the time steps have to be close enough to one another so that you can integrate from one to the other, interpolate from one to the other. So the time steps by definition have to be small. So if you're looking for 5 minutes of transient, the amount of compute time it's going to take to do 5 minutes of transient is hundreds of hours. And I'm not sure 5 minutes is long enough, Julius. I mean, you know what I'm saying? So transient analysis inside of these systems can be done, no question about it. I mean, Fluent's been doing transient for 20 years, but don't misunderstand the amount of time it's going to take to do it. And for every run, you're going to generate, 6 or 8 gigabytes of output data, and then you're going to have to assimilate each of the 6 or 8 megabytes or gigabytes across n time steps. And the time steps will be milliseconds. If you're lucky, they'll be less than that if you're not, right?
Yeah, I think that the rate of rise is, of course, a critical issue to a lot of people because they're always afraid when they lose cooling, how much time before I have to send my resume out. So it's a very good question, but you're right. From a modeling perspective, it would be difficult, and of course, and especially if you're talking about different areas of the data center. You might as well try to model your worst point, the one that's showing the weak spot in your flow to see what happens. Because
exactly
in real life, when I walk these sites, I've seen all sorts of screwy things.
Right.
That I can't even imagine what the modeling software would make out of it.
Right.
That only a little real life experience will teach you that.
Exactly. There's no substitute for experience. It never is. But what the modeler will do is allow you to create the worst case condition and try to understand it. And that's its best use. Using it as transient, the question of how much time do I have when something goes down is very dependent upon what's going down. Are the cooling pumps running? Is there water in the, in the pipes? Are there pipes under the floor? What's the conjugate heat transfer across the pipe? There's a lot of variables in there that make the whole thing a suspect with respect to real life, to a real life match. Another way to say it is we're not there yet with respect to technology. None of us. I mean, and I worked for Fluent for 20 years. I mean, we're not quite there yet with respect to understanding even what some of the physical parameters are. What's the specific gravity or heat, capacity, specific heat of a rack, or the equipment itself? It's going to absorb heat. How much heat?
Oh yeah, the mass of metal is a heat sink in one way, and it's a heat source at the same time. So it depends which way. We're trying to cool it after it heats up, and we're also trying to hope that its steady state temperature is actually acting as a sink on the way. If you lose cooling, maybe a warm sink, but it's better than 180 degrees coming off the back of the fan.
Exactly correct. So the answer to your question, Tim, is yes, it can be done, but it's computationally expensive to do it, and it's usually time prohibitive. But that'll change over time, and these things will become more cost effective over time. Okay, I think can you model rate of rise? We said that. External modeling. CoolSim does some external modeling. That's a feature that is being added more and more all the time because people want to look at the heat over the external heat exchangers. We usually do that in Fluent right now, not in CoolSim, but I'm sure we'll expose it. CoolSim is just a front end for Fluent, so we're running actually Fluent in the background. So often we'll use direct Fluent ourselves. CoolSim is just a very easy to use interface for the front end of Fluent, is essentially what it is. And I think that's it. So our contact information is here. If those of you who would like a professional hour of development certificate, please send me a note and we'll get that out to you. It is 12:59. I think we did pretty well, Julius. I'd like to thank you today for being with us on the program.
Well, thank you, Paul, for inviting me. And of course, you are offering your software service, and we are sort of your partnering in the sense of we go out to the field and look at existing conditions, and then could load with your support customers' situation into yours and come up with a solution to see if we can optimize their data center.
Exactly. All right, everybody. Thanks again. I'll post this when it's done. You'll be able to review it if you like. Our emails are attached. Let us know if you'd like anything. And everyone have a good day. Thank you.